All right. Hi, guys. My name is Robin Carball, and I am the TA for the Wednesday section between 1 and 4. You should be here for Geos 120, so hopefully you're in the right place. Here's my email if you have to get in contact with me. And I'm usually pretty good at checking my email. But if it's a weekend or something, or right before a lab is due, no promises. But besides that, I'm usually pretty good at answering emails. Right. So a little bit about the lab before we jump into how to do lab 1. Labs are found on Google Worksheets in Canvas. And I was playing around with it a bit. It seems okay to work with. It should save your work. It might be easier to copy questions over and write them in like a Google Docs or something, because I always get a little nervous. My work will be lost, but it should save it. And labs are due by 11:59 on the Friday after lab. So this lab is Wednesdays, so that Friday they'll be due. Late labs, if they're 1 to 3 days late, that's 10% off. If they're 4 to 7 days late, that's 20% off. And more than a week, I can't accept it. But I understand that things come up, emergencies come up. If that's going to happen, it's going to impact when you can hand a lab, and contact me before Friday, and we can talk about extensions if need be. But if you do miss a lab, it's not the end of the world, because the lowest overall lab grade will be dropped. There's 12 total labs, and we'll be grading 11 of them at 3% a lab. So you can either do all 12 and just drop the lowest one, or if you're just having an off week or you miss one and get a 0 on one, you can just drop that too. It's up to you. All right, so let's get into how to do lab 1. So this is for the earthquake section. And lab 1 is going to be looking at different rates of plate movement. And you should have talked about in class how the earth is split up into many different plates. And over long periods of time, they'll move, creating new land and moving around the continents. It's pretty cool. And we have 3 different types of faults: divergent, convergent, and lateral. Divergent is when 2 different plates move away from each other. We see this with seafloor spreading at ridges like here on the map and right here, where new oceanic crust is forming under the ocean here. That happens at divergent boundaries. Convergent is when 2 different plates collide, and this often causes subduction of one of the plates, which there won't be any talk about subduction in this lab, but it's something to keep in mind. And then the last type of fault is lateral faults. The lab calls them lateral faults. I usually hear them more called strike slip faults, and then sometimes they're referred to as transform faults. They all mean the same thing. It's when 2 faults rub against each other. A really common one would be the San Andreas fault in California, a fault that's sliding past each other. So the point of this lab is to look at different rates of motion on these plate boundaries and compare them to see how they relate. All right, so for exercise 1, we're going to be looking at Hawaii with respect to the Pacific plate. And so I'll go back to this picture actually. So Hawaii is right here in the middle of the Pacific plate. And it's formed over top of a magma plume called a hotspot. So what ends up happening is this hotspot or plume is down deep in the earth, and it tends to stay pretty stationary. And as the Pacific plate moves, we'll get new land, new volcanic rock forming over top, which is what Hawaii is. Right here on the biggest island, that's the current one still being built. We have that plume underneath feeding new crust. But over millions and millions of years, it's moved. A million years ago, Maui was where Hawaii currently is. And we can keep going back. So this is pointing just a path where these islands formed over top this hot spot. And so we can kind of get a rate of how much the Pacific plate is moving by calculating the difference in these islands. All right, so this lab is going to have a lot of different conversions. And it gets a little complicated since we're not doing this with paper. You can measure right off your screen, but I would just, I'd be very careful. Whatever like amount you have zoomed in, make sure to stay constant with that. If it's zoomed in 100%, like your standard screen, keep it that. You can't zoom in more and then remeasure. Your calculations are going to be wrong. But as long as you stay consistent with it, everyone should be getting more or less the same answers. So to start, for Hawaii, you'll be measuring the scale bar. So we have the scale bar here. It's 150 kilometers. And then when I measured it with a ruler on my screen, I got 30 millimeters. So this is a conversion rate, this first little part. The total scale bar, 150. I measured 30. You'll probably get something different, but that's all right. And then you can measure the island distance. So the point here to the point here. And when you do this calculation, these units will cancel out. We're just left with kilometers. The space between Hawaii and Maui is 180 kilometers, give or take. So we're going to be doing that for in between each island to get just the different amounts between them converted into kilometers. And then after that, we can graph it. And after we have it graphed, we can determine a rate of movement. So the graph is going to be age versus distance. We get age off of figure 8 right here. They all have it. Hawaii is 0, Maui is 1, and so on. And one thing to note is Hawaii has a age of 0 because it's still right underneath. It's still right over top of that hot spot. So it's still actively forming. So you can use any program you want to create your graph. I find PowerPoint pretty easy. I also like using the Google Docs drawing feature. The lab recommends using a Schotzer, which it's all right. I think it's a little finicky, but if you like it, that's fine. If you have other programs you like to use, you can do that. You can print it and draw it and then take a picture of it and upload that if that's easiest for you. As long as I get a copy of the graph somehow, you can use whatever works for you. Okay. Well, then you're going to take the distances you calculated before and you're going to plot them versus the ages from figure 8. And then just so you know, these are not correct. I just randomly put points. The only point that is correct is Hawaii at current day, which you can put at 0, 0. So everyone should have that one, but your points up here should look different. But then you could put a line of best fit on it, which should be a straight line. Don't connect the dots. That's not a line of best fit. A straight line representing the data as best as you can. And then after this, we can get a rate off of it. So Question 4 is asking for the average rate of movement in kilometers per million years. I don't know if you guys have seen MYR before, but that just means million years. Rate is rise over run. So I find the easiest way to do this is to go to 1 million years, and then you can go up to the line and then find that intersection point. So at 1 million years, the point lies at 100 kilometers. So 100 kilometers divided by 1 million years gives a rate of 100 kilometers per million years. The Pacific plate will move 100 kilometers in 1 million year. You don't have to do it at 1 though. For instance, if you want to do it at 4 million years, you would just go up, up, up to where your line is, go over. It's roughly 400. So you could do 400 kilometers divided by 4 million years. You'll still get 100 kilometers per million years. And then, like, once again, this is not the answer. It's just an example of the process. All right. So exercise 2 is calculating the offset along the San Andreas transform fault. So the transform fault's the one that's sliding next to each other. And I think the easiest way to do this is to measure the distance between the Pleistocene, Miocene rocks, and those are just names of rock ages. So we have this jelly bean shape thing. Millions of years ago, we could have assumed that they were together, and then with time, they separated apart. So that's what we're looking at. So we can do something pretty similar to question 1, honestly, measuring the distance and then getting a rate from that. So I think the easiest way to calculate this is from star to star, as long as you're consistent. Like this is the top of that rock unit, they would have been together like a puzzle piece. So don't measure the bottom to top, that would be inaccurate. But you could measure bottom to bottom if you want. I just think that's a little more confusing since there's a curve in the fault, but you can kind of average it out if you want. But I would do star to star. And then this equation's the same one I gave you from exercise 1. You can measure the scale bar here, which it gives a total of 200 kilometers. And then when I measured the scale bar on my screen, I got 55 millimeters. It'll probably be different for you, and that's okay. And then you can measure the fault displacement, which is star to star. When I did it, I got 92 millimeters. Yours might be a little different. But then when you multiply these together, you'll get the converted fault displacement. So I got around 300 kilometers. So that's saying this distance is 300 kilometers. It also asks you to do the same thing from San Francisco to Los Angeles. And that could be a little confusing since your fault is bending. Don't worry about it. Just measure a straight line, just like this, X to X here. Okay, so the last exercise, this one gets a little confusing, but I'll explain it. We're looking at the rates of seafloor spreading of the Pacific and Atlantic plates. So right here on the left side of this map is the Pacific plate, and on the right, this is the Atlantic plate. So seafloor spreading occurs often in the middle of oceans here, where new magma is coming up and it's going to push the plates apart. We call that a convergent boundary. And we can measure that spreading to get rates of movement. And let's see, do I talk about it here? Okay. So this map gets a little confusing because we have our scale bar in the middle here. But depending on what latitude you're looking at, your scale bar is going to be different. I would recommend doing all of your measurements at 20 degrees. That's going to be easiest if you do all of your measurements at 20 degrees. And if we notice on the scale bar, You're going to want to zoom in your screen to see it better. But the bottom line is for 0 degree latitude, one above is 20 degrees, 40, 60. And the whole scale bar is 1,200 kilometers. So I'd recommend 20 degrees. You're going to be looking at this second line from the bottom. And you can do the same kind of conversions. A scale bar of 1,200 degrees over top of however many millimeters this is that you measure off your screen. Okay. So the way we measure seafloor spreading, you're only going to measure half of it. Because it's forming the same crust on both sides. So we only need half the measurement where I drew these lines here. It gets a little confusing. And then each of the colors is representing a different rock age, which is given in your lab. So the first one is asking for the age of the pink rock. And it was really hard to put these lines on here. PowerPoint did not want to do it, but you would measure from the center of this pink at the 20 degree mark over to the boundary with the yellow. And I think when I did this, I got like 1 millimeter. It's pretty small. Yep, and then you can do the same calculation here. The total scale bar was 1,200 kilometers. Measured scale bar with a ruler. When I did it, I got 13 millimeters. And just be careful where you are on this scale bar, because I'd recommend doing it at 20. And then whatever your measured ridge length is, for that first one, I got 1 millimeter. So this half spreading rate will be around 92 kilometers or so for the Pacific plate. And then you're going to want to do the same thing. Start at the same point every time. These lines are a little deceiving since they're kind of moving up, but I wanted to show where to measure to without blocking the lines on you. But always do it at 20 degrees, starting at the same point. And on your map, you can kind of see like sketch marks. That's because this used to be one map that all the students would use. And when it went online, they just took a picture of it. So it's kind of a little cheat to where to start. So for the next one, you're going to start the same point and measure over to the boundary of this yellow. And you can do the same calculation, 1,200 kilometers divided by 13 millimeters times whatever that distance is. And that will be the spreading rate of the next stage. And same thing, start the same point and then go over to the next boundary, then start the same point and go to the next boundary. And that's for the Pacific plate. And then you can do the same thing for the Atlantic plate. I'd recommend going to the left again. You don't have to, but I would, just to be consistent. Yeah, I believe that is all the info I have for you. Get you started at least. And if you have any questions, please let me know. All right.